Hello, calculus fans. We're going to talk about computing triple integrals in different coordinate systems, cylindrical and spherical coordinates. And to do that, let's motivate this with an example. We'll take a solid that lies above the cone z equals square root of x squared plus y squared, and below the plane z equals 4. We'll have a picture of this in just a moment. Let's also say that the mass density at any particular point P is proportional to the distance from P to the axis of the cone. Find the mass of E. Here's the picture. So you have the cone, z equals square root of x squared plus y squared, and then you have this plane, z equals 4, and it cuts off the cone, so you actually get what we think of as an actual cone. Now if we take this solid and project it into the xy plane, then we get this region. It's a disk of radius 4 centered at the origin. Now if we describe this disk in rectangular coordinates, we get an expression like this. This disk can be described as the set of all points x, y, where x lies between negative 4 and 4, y lies between negative square root of 16 minus x squared and positive square root of 16 minus x squared. And then that means we can give a description of the solid E as the region that's above D, but between the surfaces z equals square root of x squared plus y squared and z equals 4. The cone is the lower bounding surface. The plane is the upper bounding surface. Now we're ready to give a rectangular coordinates description of the solid region E. E is the set of all points x, y, and z. The x values have to be between negative 4 and 4. The y values have to be between negative square root of 16 minus x squared and positive square root of 16 minus x squared. And z has to be between square root of x squared plus y squared and 4. Now this is a fairly complicated description of E. I had to split it into 2 lines just to get it to show up on the screen. Now let's figure out what the integrand is. All we've done so far is just describe the region of integration. Now let's talk about what we're integrating. Now our mass density function is k times the square root of x squared plus y squared. Remember that we described the mass density of this solid region so that the mass density at any particular point is directly proportional from the distance of the point P to the axis of the cone. The axis of the cone is the z-axis, and if you want to measure the distance from a point xyz to the z-axis, that's the square root of x squared plus y squared. And then the k, we throw that in for a proportionality constant. Let's write down now a triple integral for the mass of E. The mass of E is the integral from negative 4 to 4 of the integral from negative square root of 16 minus x squared to the square root of 16 minus x squared, of the integral from square root of x squared plus y squared to 4 of k times the square root of x squared plus y squared, dz dy dx. That is a complicated looking expression. Now remember, when we evaluated double integrals, sometimes we were able to evaluate them in polar coordinates and get simpler integrals. This same trick can be done with triple integrals. For the integral that we came up with for the mass, this triple integral can be more easily evaluated in cylindrical coordinates. So remember that cylindrical coordinates, we talk about r, theta, and z. So the z is the same z in rectangular coordinates, and r theta is the polar coordinates of the projection of the point xyz into the xy plane. Let's pause our evaluation of this particular integral to write out a description of how to evaluate triple integrals in cylindrical coordinates in general. So we're given a triple integral of f of x, y, z over the region E, and let's say that E is a type 1 solid region whose projection into the xy plane is conveniently described in polar coordinates. This last part, where the projection of E into the xy plane is conveniently described in polar coordinates, that's the important feature that's going to lead us to evaluating an integral in cylindrical coordinates. Let's, of course, suppose that the function f is continuous and that E can be described as the set of all points x, y, and z where x and y lies in some region D in the xy plane, and again, we want to ensure that this region D is conveniently described in polar coordinates, and then since this is a type 1 solid region, then Z can be placed between two bounding surfaces, u1 of xy, u2 of xy. And so D, being conveniently described in polar coordinates, we'll say that D can be expressed as the points r theta, where theta goes between some angle bounds alpha and beta, and r lies between two polar curves, h1 theta and h2 theta. So this is the convenient description of D in polar coordinates. Keep in mind that D is the projection of E into the xy plane. So this is what I would describe as the general situation. So what you see is that this is a type 1 solid region. You see the upper bounding surface. So this is the upper bounding surface. Here's the lower bounding surface. Then the projection of this surface down into the xy plane is nicely described in polar coordinates. So that means that we can write this triple integral over E as sort of an iterated integral. The outer integral is a double integral over D, and then the inner integral is between the two bounding surfaces, u1 of xy and u2 of xy. And since the outermost integral is over a region that is nicely described in polar coordinates, then that can be evaluated in polar coordinates. So if we do that, then we'll get this formula for evaluating triple integrals in cylindrical coordinates. So the integral over E of f of x, y, z dv is equal to the integral from alpha to beta of the integral from h1 of theta to h2 of theta of the integral of u1 to u2, and notice that in u1 and u2 we've replaced x and y with r cosine theta and r sine theta, respectively. And then the last thing to notice is that in the integrand, we've changed x to r cosine theta, y to r sine theta, and just as in polar coordinates, we have this r that just has to be put in there. It's the scale change factor. We had to do this when we evaluated double integrals in polar coordinates. The same thing will happen now when we want to evaluate triple integrals in cylindrical coordinates. So we're always going to need that r when we change from rectangular to cylindrical in triple integrals. All right, let's go back to our original problem. Remember, we started with computing the mass of a solid region, and our triple integral was a type 1 solid region. Remember that the projection of E into the xy plane is a disk of radius 4 centered at the origin, and that means we can describe D very nicely in polar coordinates. It's the set of points r theta, where theta goes from 0 to 2 pi, we're going all the way around, and r goes between 0 and 4. And the lower and upper bounding surfaces of E are z equals square root of x squared plus y squared, and z equals 4. Now in cylindrical coordinates, those are very nicely expressed. Z equals square root of x squared plus y squared can be rewritten as z equals r. And of course, z equals 4 doesn't have to change. All that means is we can describe E very nicely in cylindrical coordinates. It's the set of all points r theta z, where theta goes from 0 to 2 pi, r goes from 0 to 4, and z goes from r to 4. All right, now we're going to compute the mass of E by converting what once was a messy triple integral in rectangular coordinates to a very nice integral in cylindrical coordinates. You'll remember this was the integral that we started with, this very messy looking triple integral in rectangular coordinates. We get to rewrite this as this triple integral in cylindrical coordinates. So remember that theta went from 0 to 2 pi, r went from 0 to 4, z went from r to 4. We have to put in this r here for the scale change factor, and then our integrand turned into k times r. We evaluate the innermost integral. We'll get this expression. We plug in the z values and we get this. And we evaluate that middle integral. This is the expression that we get. Plug everything in. We'll get k times the integral from 0 to 2 pi of 64 over 3 d theta. And this is very easy. There's even no theta in the integrand. And our final expression is going to be 128 pi k over 3. You'll see that the evaluation of the integral is very easy once we convert it into cylindrical coordinates. And that's just because this particular region of integration lent itself very nicely to cylindrical coordinates. Okay, that's all for now.